Here's the outdoor unit of my heat pump. This is a 2.5 ton Armstrong unit. I'll show you some modifications that I've already made to this and a modification that I plan to make in the near future. The first thing that I changed was this defrost control right here. The manufacturer had it mounted down here on the lowest portion of the liquid line, and what I discovered was happening was, as the system went in and out of defrost, ice would build up down here. Now normally you'd think the ice would drain away, but in the somewhat harsh winters we have here, it would actually lay and freeze. Then the next defrost cycle would come, a little bit more water would add to it, and it would lay in there and it would freeze and it'd build up. And it's very common for me to see the ice to be several inches inside here in the middle of the winter. And the ice was actually up around here where the defrost control was down here, submerged in ice, and the system was constantly going in and out of defrost every 30 to 40 minutes depending on what the setting was. There was really no other way to change it. So I moved the control to the top to get it away from the ice, and that made it work substantially better. And then after that, I noticed there was some slight hunting going on in the evaporator section. Upon inspection of that, I noticed that the sensing bulb right here was originally placed over here. And as you can see, it's even before the equalizing tube for the TXV, so that was causing it to hunt. I was losing a great deal of efficiency there, so I moved the bulb over, and that made it work a lot better. And I still wasn't happy with the defrost cycles, and I modified it internally, put it on a timer so that it would shut the fan off, and I think it's set on 30 seconds. And it shuts the fan off inside, and it actually makes the entire system hunt through both TXVs and pressure equalization, so that I'm not pushing all the energy out of my house. And at the same time, I disabled the electric strip heat, so I don't have that derating factor going on in terms of efficiency. But I'm still not happy with it, even though it's working probably 5 times better than anybody else's outdoor unit. I should mention that this system is grossly undersized for my house. The heat loss of my house is calling for 80,000 BTU heating capacity, and as I had mentioned, this is a 2.5 ton unit and it heats my house. What I'm not happy with right now is the amount of defrost cycles that it has, and the fact that it actually reverses the operating mode to go into defrost. So it goes from heating mode to air conditioning mode, which changes the reversing valve right here, shuts the outdoor fan off, and it heats up the coils to defrost them. Meanwhile, the inside coil gets cooled down. So what I'm going to do is I'm going to put this valve in between the gas discharge and the liquid return. This way, this will act as a hot gas bypass. We'll bypass the internal coil. It'll eliminate most of the phase change, so I'll just be circulating hot gas from the heat of compression through the evaporator. Now this should defrost it. So now I'm just doing an overlook of it to see. I'm thinking about mounting it right here. I got to figure out how I'm going to get it in there properly without the least amount of work, and still be able to service and maintain the equipment. This valve that I got, you'll notice that it's not a external controlled valve, which means it doesn't require pressure difference to actuate. Now, the difference here is most of the valves that require the pressure difference, they'll have a capillary tube on them, which helps the internal solenoid open. Those type of valves generally have a lot higher rated hot gas defrost capacity than these magnetic only counterparts. But if I would go with the pressure differential valve, the problem may be that some future modifications I have planned may inhibit the actual valve opening. So I went with this lesser capacity valve just because I can guarantee it's going to open. This valve's rated, I believe it's at 1.5 ton of hot gas defrost, which is plenty. The reason that I'm not tapping directly into the discharge of the compressor and jumping over to the hot gas bypass is I suspect if I do this, I'm going to make, or I might take away the pressure differential which holds the reversing valve open, and it may start to hunt back and forth either way. I just don't want this to happen, so the easiest thing to me seems to be to bypass it right here. Overlook of the system, I see some slight rust starting on the dryer around some of the interconnects on the compressor. The copper tubing starting to corrode a little bit on the evaporator. I've already replaced the outdoor fan, the universal model, and it appears there may be a slight refrigeration leak right here. See how it looks very oily? That's a classic sign of a very small refrigeration leak. I may get the sniffer out here and see what it has to say. Otherwise, this is the overview of the next modification I plan to make. As a side note, you'll see a tube coming up here. This particular tube is running around the ground in my house, which I'm currently working on burying it. It's a high density polyethylene tube, and my intentions there are to tap into the natural ground wave that exists between seasons and extract heat from it. This would not be considered geothermal because I am using a natural ground wave, the heat wave. I'm not using geothermal energy. I had previously cited the movement of this wave with a hand-built temperature probe. I used a 4-foot section of ground rod and attached temperature probes every foot on it, and I beat it into the ground, and I monitored the temperature throughout the year from this probe. I was able to note the temperature moving one direction and the other between seasons, and I'm fairly certain that somewhere around an 8-inch depth is the ideal depth to be able to extract this wave. Okay, I think that's enough for this video.